Hello everyone, welcome to the numerical methods class. We are now at chapter 9, which is about the linear algebraic equations and solving them, especially by using Gauss elimination. So let's see the topics here and start how to solve the linear algebraic equations. We will give some methods. The main part is the Gauss elimination, and we will show how we use it in solving the linear algebraic equations. First of all, we will introduce the linear algebraic equations. In engineering practice, we may need to solve linear algebraic equations such as here. You can see we actually have some unknowns x's with some coefficients. You can see a values, which are equivalent to some b constants. So if n is smaller than 3, n is the number of equations actually, is smaller than or equal to 3, linear equations can be solved by simple techniques. You know how to solve these from statics class, especially you use these. If n is greater than 4, then you need to use some further advanced techniques and maybe computers to be able to make the calculations easier, because hand calculations are very difficult or time consuming if the equation number is large. We will represent these equations in matrix form. We will have an A matrix, X vector and B vector. And therefore some mathematical background is given in the following slide about the matrices. So let's check some introduction about matrices, then continue on the solving of linear algebraic equations. You remember how to define a matrix actually from a linear algebra class, but let's introduce it shortly here. We will have a matrix, for instance, which has, for example, n rows and m columns. Maybe this is wrong. This is just m columns and n rows. So these are the rows actually, and number of these is n, so n rows. These are the columns, and number of columns is m, so these are m columns. If m is equivalent to n, we have a square matrix. You can see here an equivalent number of rows and columns, and this is also called an n times m matrix. And a vector is either only one row or one column matrix. So this is, you can see multiple rows and columns, but here a row vector is only one row actually with multiple columns. A column vector is multiple rows, one column. You can see here. We can define this row vector as 1 times m and column vector as n times 1. Square matrices are important for us because the linear algebraic equations will have square matrices. That's why let's define some features of it. A symmetric matrix will have same values for the lower triangle and upper triangle, and in between there is diagonal terms. So the terms below the diagonal terms will have the same terms as the terms above the diagonal terms. And when you fold it on the direction of the diagonal, you can see here you will have the same values. For example, 1, 1, 2, 2, and 7, 7. So aij and aji will be the same. So it's called symmetric matrix. This is, for example, a 3 by 3 symmetric matrix because we have 3 rows and columns. A diagonal matrix is a square matrix where all the elements except the diagonal terms are 0. So these are all 0, but the diagonal terms are not 0. And if these terms are 1, it's called identity matrix, as you can see here. So the diagonal terms are 1 in the identity matrix, but the rest is 0. We use I as the definition of identity matrix. And upper triangle matrix, this is important in our case because we will have this by elimination approach. So the diagonal terms, if we have terms above it only and the terms below it are 0, then it is called upper triangular matrix. If we have 0 values at the top terms, actually above the diagonal terms, if these are 0, but the terms below the diagonal terms are not 0, then this is called lower triangular matrix. And there is also banded matrix. In banded matrix, we actually have all elements equal to 0 with the exception of a band centered on the main diagonal. So we have the diagonal not 0, but also additional diagonals next to it not 0, but the rest is 0. So this is called banded matrix. So here, for instance, the bandwidth, the width of band is calculated as like 1, 2, 3, 3, for instance. So this has a bandwidth of 3. This is called a special name, which is tri-diagonal matrix, we can say. Let's talk about the matrix operations in this slide, addition and subtraction. Basically, the addition and subtraction are very similar to regular numbers. We will simply add each term to each other at the certain location. For instance, we have a and b and want to calculate a plus b. We will simply, sum each term in the matrices individually. Subtraction is the same. We subtract individually each term. And these actually have the same features of the addition and subtraction of the regular numbers. So a plus b is equivalent to b plus a, as well as we have associative feature. A plus b then plus c is equivalent to b plus c then plus a. So we can use these two features for the matrix operations as well. In the multiplication, we have two cases. First of all, let's multiply a matrix by a scalar, for instance, just one scalar value, one number value. Then we will multiply each term by that scalar. Scalar is g here. So we multiply each term individually. Also, we will have a multiplication of two matrices. In this case, we need to have the same number of columns in the first matrix and same number of rows in the second matrix to be able to make this calculation. And this calculation can be obtained by this summation value. Basically, the rows of the first matrix will be multiplied by the first column of the second matrix. Then the second one will be calculated by the second column. The third row will be calculated by the third column of the second matrix, and we will have those as the result of C. This is basically the matrix operation in the matrices, the multiplication operation in the matrices. So inverse of a matrix is an important feature as well. We will have an inverse matrix of a regular matrix, which defines an identity matrix when we multiply the inverse and the matrix like this. A times a minus 1, so this is the inverse of the matrix, will give an identity matrix. But how can we calculate the inverse of a matrix? So this is not easy. For a square matrix of two-dimensional, 2 by 2, it's easy actually. We can simply use this operation. So this is basically determinant, 1 divided by determinant, and these values, 2, 2, 2, 1, 1, 2, 1, 1. Actually, the A for the A is like this here, A11, A22, A12, A21. So when we have the inverse, that's this calculation. Similar formulas exist for additional higher dimensional matrices, but those are more difficult. That's why there are more dedicated chapters, 10 and 11, for instance, to be able to get the inverse of a matrix. We will see them later. Transpose of a matrix can be important as well. For instance, for a 4 by 4 matrix, actually we want to transform just the rows to the columns and columns to the rows. So you can see here, these rows will be the columns. This row will be this second column. This third row will be the third column. Fourth row will be the fourth column. And if we have a vector, so a column vector, for instance, will be a row vector by taking the transpose of it. And transpose is shown by T. And in MATLAB, for instance, you can just use the prime value. Just use this to get the transpose. But for inverse, so it shouldn't confuse you, the inverse can be taken as this in MATLAB. So keep these in mind as well. Because in writing, we show this as the inverse, but in MATLAB, we use this to get the transpose. So please don't confuse with these. And the trace of a MATLAB is just the sum of the elements on the principal diagonal matrix. So in these diagonals, when we sum these, this is called the trace. Another feature of a matrix is augmentation. We basically augment a matrix by the addition of column or columns to the original matrix. So we have this matrix, original matrix, we add columns and we augment it. So here from 3 by 3 we augmented it to 3 by 6. So this has an expression, such an expression actually has a utility when we must perform a set of identical operations on two matrices. So we will have some operations here, but have some operations in this matrix as well. We can just simply write them together and have the same operations. This is useful for, especially for 3 by 3. If we want to take the determinant, if you remember, we can add these terms and have the determinant by using this 3 by 6. So this augmentation is useful for taking the determinant. Also for Gauss-Jordan method that we will see in the future, in the following slide, in the end of this section actually, we will add the B constants here as the augmented matrix to perform the operations together. So we can perform operations on the single augmented matrix rather than on two individual matrices with this way. After giving some information about the matrices, now we can formulate the linear algebraic equations in matrix form. If you remember, we had the systems of equations, and it has A constants, X unknowns, and B constants. So A coefficients, B constants, let's say, resulting constants. And we can define this as an A matrix. You can see here only the coefficients. An X vector, you can see here, and a B vector, you can see here. So this is an n by 1 column vector, but with transpose we can show it as row vector. Same as X, this is n by 1 column vector, but we can show it by transpose as a row vector. And we want to solve this for the unknowns X. X's are unknowns. So what we can do is we can simply use the inverse of A at both sides, multiply, and this will give us an identity matrix. So it will isolate X here, like here, and A minus 1 times B becomes the multiplication, which gives us the X unknowns. This is not very efficient because finding inverse is not easy if the number of equations is too much. Especially defining inverse is not easy, so this is not very efficient. Rather than we use some elimination methods, we will show them in the following slides.